Hello, good morning everyone. Welcome to the class 451 Control Engineering. Today we will start the last part of this course in this semester. That is digital control. All right. Okay, so ECE451. This is for the 13th week Monday's class. So we consider the digital control. Oops. Digital control. Alright, digital control. We need to start from chapter 4. 404. We start from here, and then we go back to now. We need a chapter 8. All right. Okay. So for digital control, the most case it works like this. Suppose you have a system, you have a plant, you have a controller. You have a controller. I say this is a D of S is the controller. The controller, we realize it in a digital way. That means we work like this. We have a kind of E of T go into this controller. Maybe not just controller, any kind of system. We can try to realize it in a digital way. But in most cases, this one will be a controller, not the plant. The plant itself, it will running under the analog signal. Right? Use analog signal. So this is a controller. This is a controller or something similar. Then you have, suppose you have E of T go into this D. Then we add analog to digital converter. Okay, after this we will have I denote as E D of N. So this is digital signal, discrete time signal. If here's something looks like this, now this one will be here's a T, right, for E of T. Now it's N, and there are some values looks like this, symbols. Right? Take symbols. So take symbols from it. So this one is just, you can say just take symbols, right? And then we have a discrete time system. I denote it as D with I both use D. Okay, D is D and D. The meaning different, alright. DDS. Alright. Then the output will be also a discrete time signal. Okay, I put it here. This is suppose I use U for it. UD of N. And this one, it is also something looks like something looks like this. Digital, discrete time, just a list of values. This side is N, right? U of N. Then here we use a reverse from digital to analog converter. Then we want to have a U of T. So work like this. So we will realize U of S by this way. So this part, the whole thing combined together, it is a D of S. The whole thing is D of S. So here, when you look outside, you see you have input is an analog signal, then you have something working inside, and finally you get output from here. You get it is also an analog signal. So it looks like same as just an analog system, but inside here it is running in a digital way. All right. Then in a system, usually you can have a system. You can have like you have n of s. Here, suppose you have a controller d of s. Then you have a plant g of s, and here you have a sensor h of s. Here's the input, here's the output. Then this one, and sometimes also this one. Maybe a digital one. Maybe digital. They might be digital. Maybe digital. Right. Each one you can try to realize like this way. And of course here you need a T. You need a T because you take sample, right, and you restore it. You need a T, so you need a kind of like a clock. You create a T, then this T will go to here to set up how these two works, right? Yeah, things like this. So this is a basic. You can think it's an idea about the digital control. You try to realize a kind of analog part, analog subsystems, try to realize it in a digital way. Okay. Yeah, this is I say this idea, basic idea. Then let us consider a little bit about this one, this discrete time system. Right? Discrete time system. You should have some other courses give more details about the discrete time system. So here I just gave a brief description about it. Discrete time systems. Discrete time systems usually can be written in this way. Some, like suppose y is the output, y of n plus some a1, y of n minus 1 plus until some an y a, no, not n. I use a m of n minus m, and they were equal to some b0 x of n plus b1 x of n minus 1 plus until some a capital N x of n minus capital N. Usually can be described by this way. This is called the difference equation. The difference equation. Similar with the differential equation. In differential equation, we use a derivative of a signal, right? Then you have the equation. Now we use a shift of the signal. The thing is, you know what? We have this one, y of n minus y of n minus 1. This one, you can think this one is related with y prime of t, because this is just the minus 1. It's minus 1. You divide by 1. That will be same, right? And this one you can think is just this one, right? Yeah, the slope of these is this one over this one, right? Here is 1 now, n to n minus and 1. This is 1, and here's a difference of this y, okay? And the slope is just this y prime. So you can think these two are similar thing or same thing, right? You write these in this way, then you have a difference equation. Now, of course, you cannot just write in this way. That will be too simple, you know. Okay, so this is the system can be written in this way. And then how to solve a discrete time system? To solve it, so I say this is equation. I need to put somewhere. The equation 1, alright, equation 1. To solve equation 1, we need a Z transform. Z transform. This is also similar with the Laplace transform. Right, similar with Laplace transform. It is defined by this. We start from a signal x of n by a Z transform. We can have it is a summation of x of n times z to negative n and run from negative to positive infinity. We can compare with Laplace transform. X of t by Laplace transform, it will be integral of x of t times e to the negative st dt. T run from 0 to infinity. So you see, this is summation. This is an integral. Of course, it's different. This is summation, and it's run from negative to positive infinity. This integral just run from 0 to infinity. This is one thing different. And inside, here's x times exponential power, then do integral. Here's x of n times power of z, do summation. So both of them, they have the value of x. But this function are not same. These two functions are not same. You can think this z according to e to the negative s. You can think like this. Then this is a positive. Right? This is negative n, negative t. Right? Negative n, negative t. Here's z, here's e to the s. Just things like that. Alright. So there we have this Z transform. And for Z transform, we have a very good property. If x of n I shift it by 1, what will happen? You just by definition, you do the Z transform. You will have summation. Now it's a shifted x, so here's x of n minus 1, z to negative n, and run from negative to positive infinity. And this one, I replace n minus 1. I denote this as m. Then the summation will be n run from negative to positive infinity. That will be same as m run from negative to positive infinity. And here's x of m, right? And z of, okay, n is what? N is m plus 1. So this is z to the negative m plus 1. Alright, now here I can write it as x of m times z to negative m and minus 1, right? Minus 1. I move this minus 1 outside the summation. Alright, this part is as same as the Z transform of this lowercase x. Right, this lowercase x. Oh, I need a notation. Yeah, forget that. This one we denote it as capital X of z. Right, similar. This one we denote it as capital X of s. Right, so now I write this as capital X of z. So this is just capital X of z times z to negative 1. Alright, so when you do a shift in time domain, after you do the Z transform, you go to the Z domain, it is just times z to negative 1 in front of x. This is also similar with the derivative. You take derivative on a signal and you check the Laplace transform. We have similar thing, right? You times s power in front of it. Now we times z to negative 1. If here's a n minus 1. Right? Alright, then we can solve it. Now apply Z transform to the equation 1. Y in the system, right? Then we can have y of n here y is output. All right, y is the output. The output now go to the, after the transform, go to the z domain is y of z, and plus a1. Okay, what it is? This is shifted y, so it is just z to negative 1 times y. And next element will be a2 and y of n minus 2, and shifted by 2, minus 2. Minus 2, you can consider minus 1, then minus another 1. So it's a delay times z to inverse, z inverse, and another z inverse. So z to negative 2, then y of z. Okay, until the last term. Last term we have a m, and how many z we have? We need a z to the negative m, y of z. So we have this one, and this one we're equal to, for the x part we have similar thing. This will be b0 capital X of z plus b1 z to negative 1 times capital X of z plus until plus a no, this is b, sorry, this is b. Oh, do I have any other thing wrong? Okay, that's not good. Just this should be b. Yeah, this is the coefficient here is b, not a. This is b. Bn times this one should be z to negative n times x of z. Okay, so we have y of z equal to numerator will be b0 plus b1 z to negative 1 plus until bn x z to negative n, and the denominator will be 1 plus a1 z to negative 1 plus until plus a m z to negative m. Now we have this, then times x of z. Alright, if x is given, you try to find the z transform of input. If input is given, try to find the z transform of input, then times this one, you get y of z in z domain. Then you perform the inverse z transform. Z transform inverse, you will have yn equal to something. It's just like this. So we can solve it. We can use one example to do it. Example. I have y of n minus 1/2 y of n minus 1 equal to x of n, and input x of n now is, suppose this is a 1/3 to the n for n positive. That means it is 0 for negative n. Alright, so we have inputted this one, x of n. We want to find what is y of n. Then we can use this formula. Then we have y of z equal to, it will be a fraction. You check this fraction. The numerator is coefficients coming from the input side. Now input side is just one term, right? This is b0, just it is 1. And denominator coming from the input side. Then I have 1 and the negative half. 1 and negative half with power of z. Okay, so this is y of z. This is x of z. I'm sorry. This is y of z equal to this one times x of z. Then what is x of z? X of z is this one, right? It is a summation of all the value of xn times z to negative n, and run from negative to positive infinite. Now x of n for negative n, it is just 0. So we only need a summation run from 0 to positive infinite. It is positive. And xn is 1/3 to the n, then z to negative n. Okay, then we can do a summation. This one, right, it is when n is 0, this is 1. The next term will be 1/3 times z to negative 1 power is 1 when n is 1, right? When n is 2, this is 1/3 with square and z to negative 1 with square, and so on. For this kind of things, we have formula. It can be written as 1 over 1 minus 1/3 z to negative 1. We have this one. Actually, in general, we have 1 plus a square plus until infinite. This one will equal to 1 over 1 minus a. And we have this formula. This is a geometry series. You can also prove it. It's not hard. 1 plus a square plus times 1 minus a. It will be what? It will be 1 plus a square plus all these terms, right, times 1. And minus a times it. So minus a square, right? 1 times a is a. A times a is a square. And a square times a is a cube, and so on. Then what it is? Cancel. All the rest terms, they cancel. So the answer is 1. Alright, we know this one times this one, you get 1. So this one will be 1 over it. 1 over 1 minus a. Okay, so we have this. Alright, now we can have y. Y of z is 1 minus 1/2 z to negative 1 times x. X, now we have this is 1 minus 1/3 z to negative 1. So we have this. Then we want to go back. To go back, we can have a technique. We can write this as 1 minus 1/2 z to negative 1, a over it, and then b over it. Similar, right? Similar with the z transform, we want to use partial fraction to separate it as two parts. Then you can check what are these a and b. So here's a times 1 minus 1/3 z to negative 1 plus b times 1 minus half z to negative 1 equal to 1. Then you can have different way to solve it. You can compare the coefficient on both sides. You can also plug in some special value of z. Okay, let me try some special value. I let z equal to 1/3. 1/3, so here's 1/3 divided by z. 1/3 divided by 1/3, it is 1. 1 minus 1, 0. So when z equal to this part is 0 times a, so nothing. And b times this part, that will be 1 minus 1/2. Z is 1/3. 1/3 inverse, it is just 3, right? Equal to 1. Okay, so this give us b. This is what? 1 minus 3 over 2. So it's 2 over 2 minus 3 over 2 is negative 1/2. So this is a negative 1/2 equal to 1. Alright, now we have b equal to negative 2. Negative 2. And for a, we can let z equal to 1/2, right? And z equal to 1/2. Then we have a, here's a 1 minus, z is 1/2, z inverse is 2, right? So this is a 2 over 3. This is a coefficient of a. And for b, z is 1/2, then z inverse is 2. 1/2 times 2, you get 1. 1 minus 1, you get 0. Okay, so that's 0. Equal to 1. So we have a times 1/3 equal to 1. A equal to 3. Equal to 3. Alright, we know y of z can be written in this way. And then we want to go back to the frequency domain. From frequency domain, from z domain to the n domain. Okay, we try to find this one. 1 over 1 minus 1/2 a z inverse. Use the inverse z transform equal to what? we know by definition this is some summation of x of n times z to negative n according to the sequence x of n, right? So we will try to rewrite this in terms of this one. Then the coefficients will be this part. Okay, then we use a long division, 1 over 1 minus 1/2 z to negative 1. And put the 1 here. This is 1 minus 1/2 z to negative 1. Then I subtract 1 minus 1, you get 0. 0 minus this part, I get half z to negative 1. Alright, then I plus half z to negative 1. I will have half of z to negative 1 minus 1/4 z to negative 2. Then I subtract them. These two cancel, and this part will be 1/4 z to negative 2. Okay, then I plus 1 over 4 z to negative 2 here. Okay, then I can have this one times this one. I get 1/4 z to negative 2, and minus half and 1/4 is 1/8 z to negative 3, right? You times the power together. Okay, so when you subtract these two, you get a positive 1/8 z to negative 3. Alright, now you should know the rules, right? Next will be 1/8 z to negative 3. And then 1 over 16 z to negative 4 will follow, and so on. So this part is what? We have this 1 over 1 minus 1/2 z to negative 1. We do the inverse, the transform. We will have 1, 1/2, 1/4, 1/8, 1/16, and so on. You can just write these as 1/2 to the n times the unit step at n, just like this. Alright, yeah, this is just unit step function, but here is not all the time. We just put the integer inside. Yeah, we have this one. It's 1/2 to the n. N were increasing. Okay, 0, 1, 2, 3, 4, and so on. So this one can go to this one. And then we go back to our problem. Y of z is summation of these two. And each one go back to the n domain, the time domain. There will be 1/2 to the n. This is also 1/3 to the n, right? It will be this one. It will be this one. So we can have this is in n, in time domain. Y of n will equal to a is 3, a is 3. Then this part go back to the time domain. There will be 1/2 to the n times u as unit step at n, and plus b. B is negative 2, negative 2. Then this term, it is 1/3. Similar way with this one, just here replace 1/2 by 1/3. So you can have this is 1/3 to the n times u as of n. So you can have y of n looks like this. Alright. So by this way we can solve the digital system, discrete time system. And here the key formula we need to use is this one. 1 over 1 minus sum a times z to negative 1. If we perform inverse z transform, we will have a to the n times u as of n, unit step. So the key is this one. The key is this one. Now when you have z transform, usually it's a fraction like this. You try to separate it as several part. Each part is a constant over 1 minus some a z to negative 1. Then you plug in this part. Then you get your answer. You get the answer. So this is a kind of general way to solve a system solve a discrete time system. And here the important thing is that function. We go back. This one, this function, we call this the transfer function. Transfer function. That will be same with the transfer function, right? In analog system. That is in S. This is in Z. This is in Z. You can denote it as like G of Z, things like this. G of Z or D of Z, yeah, whatever. Yeah, you can denote it by this way. Okay. Now with this as a background, as a basic tools, then we can try to work. We can try to work for the digital control. Now consider for a digital one, we consider this one. How to realize how to realize the system. Which system? Okay, we start from simplest one. Realize the system 1 over S by a digital way. It works like this. We have 1 over S. This side is E of t. This side is I say just a U of t. 1 over S actually should be an integral, right? Integral. So this one, U of t, it is just an integral of E of t. I say d tau, and tau run from 0 to t. Okay? This is a function of t. It is this one, right? This is one simple one. Now we realize in a digital way. We have this E of t. We need an analog to digital converter with a t, with a period t. Then here we have E of n. What is E of n? E of n is E of nt. I put a d here. Ed, digital one. Ed is a digital one. Discrete time one. It is E of t, but t is n times capital T. Capital T is given by you as a step to take samples. Alright. So E of d, Ed of n is this one. This one. And this one, then we go into a system. Go into a system. I still use the transfer function to denote it. I don't know what it is. I just say this is a GD of Z. We won't find it, right? Then output will be some, I say it's a UD of n. Then UD of n, we do a digital to analog converter. We will have Y of t. Right. We have this. Now Y of t, now is U of t. U of t. For the same E, we want find GD of Z. Okay, I still use Y of it. So that Y is just U. Okay, so this is a digital one, right? We find the digital digital system, discrete time system, and we connect these in this way, an AD converter, then go to this digital system, then DA converter, we get the output, and this output just as same as U of t. Now of course maybe you can only have something approximate to U of t. Now what is this D? This is GD. What is a GD? Any idea? Okay, here is GD. Actually, it is you see the transfer function of a system, right? When you consider a system, you can have this transfer function. It is just based on this relation, right? Based on this relation, you have this relation, this difference equation of input and output. Then you can have this transfer function very easy. So you need to check this part, and okay, we work like this. ED, right? We have ED of n. Then we go into GD of z. This side will be UD of n. We want this one related with U of t, right? U of t, which is this one, 0 to t, E of tau d tau. Now we want to rewrite this part in terms of ED. Now, ED is this one. ED is E of t, and t equal to n times capital T. You take sample from E, right? E is the input here. Then you take samples, you get ED. Then by this digital system, you have output UD. You want UD can go to UT. So from here to here, you can just suppose it looks like this. You have some U of t and UD of t. They are related just as this. UD of n, they are samples of U of t. Then you think you get U of t. You get U of t. Alright. Then what is a UD? UD this one. Then I can write this one. UD of n. I want this equal to U of nt, right? T the step, nt. And U of nt is 0 to nt, E tau d tau. I want to rewrite this in terms of ED. So this part I can write as this is nt. Okay, I run it as 0 to n minus 1 times t, and E tau d tau, and plus here's n minus 1 t to nt, here's E tau d tau. I write it this way, right? And what is this part? This is just the integral of E. You get integral of E, you get U, right? So this is U of t is this one. So n minus 1 t. So it is just U of n minus 1. Alright. Yeah, it's UD, sorry. UD of n minus 1, right? This part is UD of n minus 1. And what is this part? What is this part? You can say this is a t. Here's nt. Here's n minus 1 times t. Here's n times t. Right? And each point you have a value. Yeah, I just put two values. Maybe this one is smaller. Right? Now I just put it like this. This one is larger. Then this is the E of tau, right? E of t. E of t will be a curve looks like this, right? And this part is just the area, right? This area, this integral, it is just this area. It's just this area. And what is the value of this area? We can try to connect these 2 points as by a straight line. Of course, by this straight line is not the curve. We have some small arrows, right? The curve of the function is this black line. The red one is just connect these 2 points by a straight line. But you can see the area below them, they are quite similar. The arrow is very small. Arrow is just here, right? Arrow is just here. So the arrow is very small. Then we can say this one approximate to the area of this part. So the length here is t, right? This length is t. Approximate to t times, and this part I needed the average of these 2 values. Average of these 2 values, right? Yeah, it should be the area should be like this, right? You remove these to here. So the whole area, and with this rectangle, this should be same. We should have same area, same areas. And this one is what? This is t times the average of these 2 values. That is divided by 2, and this value plus this value. They are just the e of n minus 1 plus e of n. So we have this one. Okay, then this one equal to this one plus this one. Oh, this is ed. So we have ud of n equal to ud of n minus 1 plus t times ed of n minus 1 plus ed of n over 2. Alright, now the input output is E is input, U is output, right? E input, U is output, U is output, ED is input, UD is output. And then we move the output in one side and output in one side and input in another side, t over 2 times ed of n minus 1 plus ed of n. Okay, then we have the transfer function. Transfer function. This side is u, this side is e, so ud over ue. That will be t over 2 times okay, this is a fraction. This is a 1 delay, this is no delay, so it's 1 plus z to negative 1, right? And this is a no delay, 1 delay, is 1 minus z to negative 1. So we have this. U over, sorry, this is ed. That's ed. Too many notations. ud over ed. I got this. Okay, then what do we want? We want okay, see here. This part is u to replace this one, right? So 1 over s, now you have in z domain you will have the u to d, you need this one. So the system is 1 over s. This is in the analog system, right? Analog system. Then according to 1 t over 2 times 1 plus z to negative 1 over 1 minus z to negative 1. This is a digital system, the transfer function. In other words, when you have 1 over s, you should have this one. Okay, this is just for 1 over s. When you have a more complex system, you just replace 1 over s by this one, that will be fine. We know the structure, right? Recall what is the structure of system. The system can be built by 1 over s, a constant gain, or a summation. As for constant gain and the summation, you do not need to do any change. Just change 1 over s to this one, that will be fine. And you can also say this is s according to, just reverse, this is 2 over t times, here's 1 minus z to negative 1 and 1 plus z to negative 1. So like this. Okay, actually this is our first method, how to design a digital field. We just replace all the s by this one. So okay, for a given system, I will say I use G, okay, G of S, we use the following. To replace it, I have analog to digital converter, then GD of S, and then DA converter. Now we use this one to replace that one. Where? Okay, I need both. I need the same T, same sample T, same step T to take samples. Where GD of S, GD of Z is in the digital one. GD of Z will be defined by G of S. Just replace S by this 2 over T times 1 minus Z to negative 1 over 1 plus Z to negative 1. That's it. Okay, so we can have we can define the digital controller. This is a digital controller, right? And we have a name of this method. It is two-string method. So we can just replace all the s by this one. Then we have the digital one. All right. Okay. This is that we check this, right? We check this. Now here we have some impulse, some digital values, some discrete signals. Then go to the DA. What is the DA? Actually, what is the AD? Right? In more detail. The AD, you can think it is just a switch. It's just a switch. The switch on and off with certain period. Then a signal looks like this. Then here will be, okay, a pulse go across it, another pulse go across it, pulse go across it, a pulse go across it, a pulse go across it. It just looks like this, right? Yeah. Then you have a sequence of values here, depending on you can measure like the power of those peaks or the voltage of this peak of this pulse. Every pulse you measure the voltage, then you have a sequence of values. So this is AD. Then for DA, what is the DA? Now you have a sequence of the value, right? You only have this value. You can see they are parts, sequence of parts. Then you want to go to the other side. You want to have this is continuous. This is T. This is N. Now this is N. you want to give a continuous time signal. Now how to get it? The most simple way is just like this. You have value here, then keep it until next value coming, then keep it until next value coming, then keep it. It just look like this, because this is a zero hold. Zero hold means zero here means an arrow without any arrow. When you get a value, then you just hold it, use this value, keep it in no change, then you have a straight line. And when you get the next value, okay, keep this value again, zero hold without any change, just hold it, hold it, hold it, hold it. Then you have a continuous time signal. This is a signal, analog signal, right? When t change, you have different values. And of course, this one and the original one, they are not exactly same. They are not exactly same. You have some arrows, right? The original one is like this, so you have some arrows. But when the t is small enough, it is good. It is good. Actually, for this part, we have some other method. For example, you can use we call it or by the interpolation. Interpolation. That means when you have these values, you try to connect them. But usually this kind of method, you need some time delay, because when you get this value, you do not know what is next, right? You can maybe go up, maybe going down, so you need more information to get this value. So yeah, you can have some, you can wait until next value come in, then okay, this one is a reasonable choice, so you just keep no change, right? You can also use some previous values to do some calculation and estimate, okay, this line might be something looks like this. You can try to connect it, but how to say, you need some time cost times. So I would say most common use is just zero hold. It's simple and useful. Then the thing is how to choose t, right? Every t you pick a sample. Usually t is larger than 20 of the bandwidth. So when you consider system, the analog system, and you need some signal go across it here, right? Turn around here, you have signal. Now all these signal, they have a limit of the frequency band. Then that bandwidth, you choose t larger than 20 of the bandwidth. Then smaller, frequency is, so 1 over t larger than this. Yeah, 1 over t, the frequency, 1 over t larger than this. That means every second you need more samples. The sample rate were larger than the 20 of the bandwidth. Then the arrow will be small. The arrow is you still have arrow, but this arrow is fine. You don't think this arrow will give you some big mistake, right? Okay, so this is the testing method, anyway, testing method, right? Okay, then we can check an example. I can use my lab to run an example to see how it works. Okay, yeah, let me write a file so I can save it. Right. I write a file and go to the Okay, I try I use a function just ECE451. This is the Monday's class of the 13th week. Okay, can I just use this as a name? Doesn't matter. Okay, I just use the name. Testing. It's my testing. Okay, we want a system. We want one kind of system, just any one. Let g of s, it is a transfer function. I use s. I define this one. S equal to transfer function of this one. Okay, then I use this s to define our gs. It is okay. First one, just consider the first simple case, the most simple case. 1 over 1 s minus s plus like 3. Alright, so this is system, right? This is system, and we can see what is the step response of it. And then we want to take sample. I need a capital T as a sample step. For example, I choose this is point 2, and then I will replace GZ. This is GZ, the digital one. GD is digital one. Digital one will be 1 over. Oh, I need a Z. Okay, I need a S. I need a Z. Oh, this is continuous. For chance, I forgot. Maybe I don't have it. Okay, let me write something. Example. G of S is 1 over S plus, which one I just posted? I just put it 3. Right. T equal to 0.2. Okay. Right. I have this one. Then GD of Z, it will be replace S by T over 2 times the formula 2 over T times 1 minus Z to negative 1 and 1 plus Z to negative 1. Alright, so this one now S is 2 over T times 1 minus Z to negative 1 over 1 plus Z to negative 1 and plus 3. Okay, then I multiply this part on both numerator and denominator. I get 0.2 times 1 plus Z to negative 1 is a numerator. Denominator is 2 1 minus Z to negative 1 plus 3 times this 0.2 and 1 plus Z to negative 1. I keep this T. Alright, I keep this T so I can change the value when I run the program, right? I don't know, so I just type this. So here's divided by T. Then I don't need this, right? I just times 1 plus Z to inverse in both numerator and denominator. Then here's 1 plus Z to negative 1, and the denominator, the constant term, I have a 3 and 2 over T. And for Z inverse, Z inverse, I have 3 minus 2 over T and Z inverse. Okay, so I have G of D, this one. Then we can define. Okay, let me go to here. Then G of D, I have numerator is a field. field. Then the numerator is just 1 and 1. And the denominator, I have 3 plus 2 over t. And the 3 minus 2 over t. Alright, this is GD. Okay, then I have both systems, and let's see the step response of them. Alright, so I put them in the same picture so I can, we can compare them, right? Figure 1, and hold on. Then step of G of S, and the step of G of D. Alright, it's wrong. F5. Yeah, I need to save it. And let me run here. And run here. Right. Testing. Okay, something wrong. Line 8, 27. Line 8, 27. This one, oh, this one. Some mistake. Okay. Something wrong. I can run it from the editor. Now it's from the command window. It's fine. Okay. What is the T? Put the wrong T here. Oh, T is 0.2. T is 0.2. And the wrong again. T is 0.2. I need to save it. Which one? So I need to close. Okay. Let me put the close in front in the beginning. So close, or then all the old graphs will be closed. Okay, the blue one should be the analog one. The green one should be the digital one, but it should not match. Okay, I got something wrong. Let me see. I run this transfer function and the T is this, and transfer function, sample time unspecified. I need to set the sample time, you see? Yeah, here the digital one just use every one as a step, right? 1, 2, 3, 4, 5 is here. This is 5, right? So every one as a step, but we should use T as a step. Then I need to change it here. Yeah, I put the T here. Alright, I put T here. Okay, now I can run again. Say, and run it. Okay, now it's good, right? So the blue one is the analog one, and the green one is a digital one. Of course, they have arrows, but it works well, right? It works well. They use the same way. And if we change the T, if we change the T, here T is 0.2. If I 0.02, then 10 times more samples, right? Step is 10 times less. Then the samples will have 10 more samples in each second. And let me run. Did I save it? Save it. Okay. Then run it. Yeah, it's quite good, right? The digital one and the analog one, they're quite similar. So this is quite good. Yeah. Okay, this is one example, and we can see more. Like, I think I can have a function. Can I try this? T TF field FT. I can define S, right? Oh no, transfer function. Here, transfer function. I think I can also define Z by this one. I can define S. I know S is this one, right? This one can define S. Can I define Z? And then define Z. Oh, is it? Oh, okay. I can also define Z. I can define Z. Then I can write a program more convenient. You know, we do not need to calculate this. I can just use S is this, and I put T in front. I put the T here. Then I define Z equal to the transfer function. Transfer function of this is a Z with a step T. With step T to take sum of. So I have Z. Now I can write the function, transfer function, just use S and Z. So like this is G of S, then G of D. G of D I can just use 1 over. Okay, here's S plus 3. I replace S plus 3 by what's the formula? Is T over 2. Okay. Is T over 2, T over 2 over T, yeah, T 2 over T times 1 minus Z to negative 1. I can use this one, Z minus 1, right? Z minus 1. Z minus 1 over Z plus 1. The same thing, right? Z minus 1 over Z plus 1. The same thing, right? Okay. I use this for S. This for S. S plus 3. Then I can use this one to replace this one. Then by this way, I do not need to calculate, right? Here, like I write all the process to find the final answer. So, but I use this variable Z. I can write GD just by this one. And let's run. Did this work? Save it. Function. Okay, same thing, right? Same thing. So by this way, we can save a lot of time to calculate, right? Okay, then we can try some different things. For example, if I have this is I change this to be S plus not capital, lowercase, S plus 1, just S plus 1. So I have this is a compensator, right? And then I add this part for S. So this is a S plus 1 in the numerator. Okay, I have a different GD. Then I can also run it. F save it, run it. Okay, it also works, right? And I change it some larger T. This T is too small, we can't see. It seems the graph is almost the same thing. I make some change. I use a little bit larger T, I use 0.2. Okay, then I save it. I run it. Okay, this one looks like this, right? Looks like this. The green one, the steer likely. This is a digital one, and the blue one is a curve. That is a continuous one. They are quite similar, right? Okay. All right. By this way, we know how to do it. Actually, in MATLAB, they have a command. It is a C to D. C to D. How to use it? C to D is a continuous time to digital one, to discrete time. Yeah, C to D, convert of continuous time model to discrete time. So I put system, put the step, put a method, and we have several methods. And okay, so here we already studied this testing method. We have testing method, and another name is bilinear approximation. So this one we have two names. You can call it as testing. That is the name who first one introduced this method, and you can also just use bilinear. This is because this is a fraction. Both numerator and denominator is linear, so we'll call it bilinear approximation. This is a name related with refer to the method. Right? You can use both methods, but you put this one in your function. You can get the result by MATLAB. So this is GD. I give a GD2, which is a C to D from GS by step T, and use method testing, right? TUST, testing. Alright, and we can see the step of GD2. This should be nothing, because it's same curve with previous one, so you can't find it. They are totally same. Okay, run this. Alright, you see, actually we have three curves. One is the one is green one is red one. They are totally same, so you can only see the last one is green, the last one is red one, the green one is covered. Here you can see the green. Alright, and the blue one is the analog one, and you can also see the result here. When I run this, I use this T, and this is the transfer function when I define G of S. Right? You can compare with the code here. Yeah. So this is when I define G of S. I define G of S, and then I define GD. GD is this one. Right? This is the GD. I define GD. Then I put all of these. Then MATLAB calculated, give us this result. And later I use the building function. I define another GD. Then they give a function looks like this. The function looks different because the last one it canceled the unnecessary terms, and this one you see the second order. It's the second order. Our system is the first order, right? First order. Yeah, our first system is the first order. Right? The result should be first order, but when the computer do the calculation, they do not cancel anything. They just keep everything there. They do not do simplify. Do not cancel anything. So you get a second order. Right? It get a second order, but it should be same. So this one, and this one, these two GD, they are same thing. When we check the step response, they are totally same. All right. Okay. That's all for today. Then see you next time. Bye bye.